Good morning, students. My name is Dr. Mallikarjun, working in Institute of Aeronautical Engineering, Department of Information Technology. As a professor, I am working here. In the series of lectures in the operating systems, today, lecture 9, Classical Problems of Synchronization. See, last videos, I have explained about process scheduling, what is process versus thread, context switching. Those videos mainly explain focus on process. Two or more processes are executing at a time, it leads the process synchronization. Under this process synchronization, what are the various problems comes under the synchronization? See that classical problems of synchronization comes under first one is the bounded buffer problem. It is also called producer-consumer problem. Second one is the dining philosopher problem. Third one is the readers and writers problem. Last one, sleeping barber problem. So other than these, various problems are there, but these problems are popular. Let me check bounded buffer problem. So bounded buffer problem is also called as the producer-consumer problem. This problem is generalized in terms of the producer and consumer. Producer is the one and consumer is the one. At the same time, bounded is the one part, buffer is the one part. Let me two part. So, how producer produce the item, how consumer consumes that item. This is the problem. So, the solution to this problem is to create two counting semaphores. One is full and the second one is empty. These are two semaphores. One is full semaphore and second one is empty semaphore. So semaphore is a protected integer variable that allows one of the process to enter into its critical section. To keep track of the current number of full and empty buffers respectively. So producer produces a product and consumer consumes that product, but both use of one of the containers each time. So the bounded buffer problem discussed in detail here. See the picture in this bounded buffer problem. In bounded buffer problem, there are three entities, storage buffer slots. Consumer and producer are 2 points. One is entry point and one other is the exit point. The producer tries to store data in the storage slots while the consumer tries to remove the data from the buffer part. One is the storage part, and one is the buffer part. The producer tries to store data in the storage slots, means this comes to as a producer part. Consumer tries to remove the data from the consumer part, like this is the buffer part. This means producer comes under bounded part, bounded, and the consumer comes under the buffer part, buffer. Let me check. There are various slots, buffer slots. Let me take one, buffer slot 1, buffer slot 2, so on, n slots are taken. The process goes to the next, means it is going to be ready for the producer to produce the item. So, keeps on produce at one end, consumer consumes that another end. This tries to store the data, storage slots. Let me take n number of slots in between that producer and consumer, in between that like bounded and buffer. So, this problem can be solved by the semaphore, like full and empty semaphores. So, wait semaphore and signal. These are two functions. Let me check the code here. Wait and signal. Those two functions working with the semaphore as an variable like semaphore s. While s is equal to 0 means that there is nothing should be there. Once this condition is a true, S is 0, this condition is true, S should be decremented by 1, means should wait. When immediately that signal starts, that producer comes, immediately signal starts, S should be incremented by 1. Means that the bounded buffer problem uses semaphore. So that semaphores here proceeding with the make to sure that the process to data buffer is only either producer or consumer. When producer is placing the item in the buffer, consumer should not be consumed. So this performed with the mutex algorithm. Like mutex used to lock and release the critical section. Like mutex function empty and full. Empty keeps tab on number empty slots in the buffer at any given time. Initialize yes as a null, as a all slots are empty. Full keeps the tab on number of entities in the buffer at any given time, that is initialized to 0. Let me check the next problem comes under dining philosopher problem. Actually, bounded buffers are problem solved by the empty and full functions, by using semaphore and empty and full functions. But in the same way, we solve this problem, another problem, this is a dining philosopher problem. See the picture, a philosophers sitting in the dining table and eating the food. See, the dining philosopher problem states that K philosophers seated around a circular table with one chopstick between each pair of the philosopher. See, philosopher 1, philosopher 2, philosopher 3, philosopher 4 and philosopher 5. These philosophers and between the two chopsticks in between these two philosophers. A philosopher may eat if he can pick the two chopsticks adjacent to him. One chopstick may be picked up by any one of its adjacent follows, but not both. One philosopher take one left chopstick and then eat and then starts thinking, means that the right chopstick is empty. The other philosopher immediately pick the right chopstick and starts to eat. This problem involves the allocation of limited resources to a group of process in a deadlock free, and this problem also goes to the starvation. Starvation is the situation where one philosopher keeps on eating, could not give in the chopsticks to another philosopher. It's a long time for the execution. That is problem of starvation. So deadlock free is nothing but a starvation free. So let me discuss dining philosophy problem in detail. Yes, see the figure. So all philosophers take chopstick at a time. Each process goes to the deadlock. So here I am completely given as a figure, animated figure shows that there are 5 philosophers. There are 5 philosophers sitting in this table. Philosopher 1, philosopher 2, philosopher 3, philosopher 4, philosopher 5. All philosophers take the chopstick at a time. It's the problem leads to the deadlock. So that what we will do. So to solve this problem of the dining philosopher problem, let me take a chopstick. One philosopher take one chopstick, then another philosopher takes the one direction angle. See, this is the wrong. C1 philosopher, C0 philosophers take P0, C1 take P1, C2 take P2, C3 take P3, C4 take P4. Again, C1 take P0. This is the cross mark indication. That cross mark indication leads to deadlock. See, here P0, P1, P2, P3, P4 are philosophers. Chopsticks are C0, C1, C2, C3, C4. Let me take a clockwise direction takes all philosopher one chopstick at a time. then C1 take 2 chopsticks, then its problem leads to a deadlock. So, a dining philosopher problem can be solved by using the process P by the sample code I given here. I collected from the sample code in the Geeks for Geeks website. I given this material collected from the Geeks for Geeks. So the process Pi, while true, do think. Think once think philosopher, then pick up the chopstick. That is the function. Pick up function is a chopstick you can collect. Pick up function. Chopstick I plus 1 is modified. Then goes to the function, goes to the eat function. Eat function starts. Once chopstick comes to eating, then philosopher goes to think. Then again put down the chopstick function should activate. Chopstick I plus 1 mod 5. So this is a solution of the philosophers to take the to consider the problem of the dining philosopher. See this code activated by the following diagram once execution. This code can be starts executing. So this can be solved by the following the representation of the diagram. Solution of the dining philosopher problem. This is the solution figure. This figure gives the solution. Let me take the how the chopsticks can be changing. We seen in this figure. See the philosopher take 2 chopsticks. Another philosopher should wait. So the 2 philosophers only chance to eat. Let me changing the chopsticks for 1 philosopher to 1 philosopher. How we've seen in this figure. This figure gives the animation to solve the problem of the dining philosopher. There is a chance at a time 2 philosophers only can eat. Remaining philosophers should start thinking. Then chance to another 2 philosophers can start thinking. Another 2 philosophers starts eating. So this is the solution of the dining philosopher problem. So comes to the reader's writer's problem. So we've seen the solution of the dining philosopher problem. We've seen the solution of the bounded buffer problem. In the same way, similar fashion, there is a problem of the reader's writer's problem, and solution also similar to the previous problems of this problem, reader's writer's problem. Suppose that a database is to be shared among several concurrent processes. Some of these processes may want only to read the database, whereas others may want to update the database. We distinguish between these 2 types of process by referring to the former as readers and to the later as writers. Readers are different and writers are different. First, readers can take place, then writers perform what readers has did. Precisely in operating system, we call this situation as the reader's writer's problem. In the database, readers are and writers are came the situation at a time. This is the synchronization we see in the readers and writers. To share between readers and writers, then only we can solve the solution of this problem. So, this problem parameters we see here, one set of data is shared among a number of processes. Once a writer is ready, it performs its write. Only one writer may write at a time. If a process is writing, no other process can read it. If at least one reader is reading, no other process can write. Readers may not write and only read. These are the parameters we seen in the reader's writer's problem. We shared the data among the number of processes. Those who find out who are readers, who are writers. Once writer ready, it performs write operation. Once process is read, it perform goes to the read operation. Let me see the readers writers problem. To solution is similar than by readers writer problem by using the semaphore and by using signal and wait function is similar to the bounded buffer problem. Coming to the sleeping barber problem. In the barber shop with one barber chair and n number of chairs to wait in. When no consumers are there, the barber goes to sleep in the barber chair, and must be when consumer comes in. When barber is cutting hair, when new customer takes empty streets to wait or leave the vacancy if no customers are there in the shop. See the diagram. The waiting chairs are many, but customers entering is one end and leaving is also in one end. If no customers are there, that hot chair sleeping, the barber sit and goes to sleep. If customer is there, the barber starts cutting the hair. This problem also similar to the bounded buffer and producer consumer like readers writers. Similar problem. We can solve this problem by using a semaphore and by using wait and signal functions. So this problem can be situated as a synchronization. When more number of customers came into the shop, the problem goes to the start synchronization. If no barber is there in the shop, no customer is there in the shop, the barber sitting in the hard chair and is going to sleep. So to solve this problem by using semaphore. Semaphore is very important variable that allows one process into the critical section. Let me start writing the code wait. So wait means we initialize this function with the semaphore. Yes, means that in the wait has been there, the semaphore should be decremented by 1. Means the barber has to wait if no customers are there. Means that barber sitting in the hard chair and going to sleep. Whenever the customer came into the shop, immediately the signal function should be activated. Signal, the semaphore, yes, should be there. Then the customer is there in the shop, the signal semaphore, yes, should be activated and this should be incremented by 1. Because the customer is there, the barber might be active and start to cut the hair. So these images I collected and I given the link also. This problem solution is also available, detailed program available in that link. Could you go to that link and search the solution of that problem? Means that you can execute that program, you can immediately see that what are the customers are should be wait and who are the customers should barber can work, and once the customer completed their work and then immediately leave the shop with problems. So okay students, thank you. We seen this thank you from this lecture. We seen this producer consumer problem and bounded buffer problem, sleeping barber problem and readers writers problem. We've seen all the problems of the synchronization. So okay students, thank you.
Like, share and subscribe. Hit the bell icon for more updates.